All right, hi everyone. So today we are on Unit 7, Day 3 and 4. So hopefully those notes have been passed out to you, the 7.7 System of Inequalities and Linear Programming. So today you're going to be watching this video and taking notes on the provided note packet. Pause this video if necessary, repeat if necessary, and then once you get through the notes and your whole group is done, move your desks into groups, talk through the notes, any questions you have, work it out together, and then you have the rest of the period to work on your homework. If you would like graph paper for the graphs, especially for the 7.7 homework, I have graph paper at the front of the classroom on that table that's pushed up against the windows. Help yourself to as many of those pages as you would like. All right, let's get started. So today we are doing, starting out with system of inequalities. So our objective today, by the end of class, you should be able to graph a system of inequalities, including finding all vertices and overlapping shaded areas. So when you are graphing an inequality, your answer is no longer just a curve. Your answer is an entire shaded region. And your actual curve might be part of the answer, might not. It depends on the inequality symbol. So if you end up having a greater than symbol or a less than symbol, your curve is not part of the solution. It's everything strictly greater than or everything strictly less than. So you use a dashed line to represent, hey, everything up to this curve. Whereas if you have a greater than or equal to symbol or less than or equal to symbol, then your curve is part of the solution, and we represent that with a solid line. Now, in Math 1, 2, 3, when we did inequalities, we primarily checked inequalities by testing a region. You would pick a region. So for example, if we have this line, I have two possible answers, either this region here or this region here. So you would pick a point within one of the regions. I picked a point in region A, plug it in. If it gave you a true statement, then you knew that that was the answer. If it gave you a false statement, then A was not the answer, therefore B had to be the answer. But there's actually a quicker way to test regions, and that's by solving your equation for y, and then if you have a greater than or equal to sign, you shade above. If you have a less than or equal sign, you shade below. But it is imperative that you solve for y first. So let's take a look at our first example, a system of two linear inequalities. I'm going to take that top equation and I am going to solve it for y so that I can graph it in slope-intercept form, but also I can use that shortcut. So I have x minus y is less than or equal to 4. Subtract the x over, divide by -1, and remember, when you divide or multiply an inequality by a negative, you have to flip the direction of the inequality sign to account for your positives becoming negatives and your negatives becoming positives. So we end up getting y is greater than or equal to x minus 4. So our y-intercept is 0, -4, 1, 2, 3, 4. And our slope is +1, so up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. And remember, you always go to the right. If it's positive, you go up to the right. If it's negative, you go down to the right. But always to the right. Solid line to connect these points because greater than or equal to, so our line is part of the solution. And instead of testing a point, I'm going to use a shortcut. We want where y is greater than, so that means everything here above, the region that's above my line, because that's where everything's greater than. And now our other line, y is greater than -1, that is a horizontal line because we have no x, therefore slope is 0, so a horizontal line. Dashed horizontal line because we want where y is strictly greater than 1. So my answer to the inequality ends up being this shaded region here. That is above the dashed red line, above the solid purple line, meaning any point within that region is a solution to both inequalities. So for example, 0, 0 is in that region. If I were to substitute in 0, 0 to both equations, I should get a true statement. So for example, if I substitute 0, 0 in for the top one, we get 0 is less than or equal to 4. That's true. If I substitute it into the bottom one, we get 0 is greater than -1. That's true. So that entire shaded region is our solution. This shaded region here is a solution only to y is greater than or equal to x minus 4, and the solution here is only, any point in that region is only a solution to y is greater than -1. And this region here, any point in there is a solution to neither inequality. All right, our second one, we have a line and we have quadratic, so let's start with that line. Y is greater than 1/2 x minus 6. Our y-intercept is 0, -6. 1, 2, 3, 4, 5, 6. And our slope is 1/2, so we're going to go up 1, right 2, because we have a positive slope. So up 1, right 2, double reverse. Dash line, because we have strictly greater than, and our shaded region is up, because that's where y gets larger. Our second inequality, our quadratic inequality, it's quadratic in vertex form. Vertex is at 0, 4. A value is -1, so our parabola is opening up down instead of up. Remember that pattern of A, 1, 3, 5, so we go down 1, put a point, down 1, 2, 3 from there, put a point, and our symmetric point to match, and then down 1, 2, 3, 4, 5 from there, put a point, and our symmetric point to match, and a solid line because it's less than or equal to, and then we shade in between because that's where y is less than versus up here, right? We wouldn't shade up there because that would be greater than. So our answer to that system is this region here that is below the quadratic but above the linear inequality. So any point within that region will be a solution, and if we were to test that, 0, 0 is in that shaded region, so let's test. If I substitute in 0, I get 0 is greater than -6, true. 0 is less than or equal to 4, true. If you did not follow that pattern of A for quadratics, you might want to look it up, or you might want to come see me during one of my office hours. I'll gladly go through that again, but that is something you learned in Math 2, or is hopefully reviewed again in Math 3, that I'll gladly go through with you one-on-one if you'd like to come see me during my office hours. All right, number 3. For a concert event, there are 30 main floor tickets and 20 balcony tickets. There are up to 2,000 main floor tickets available, and fire regulations limit the number of concert goers to 3,000. The promoter must take in at least $75,000 in ticket sales. Find a system of inequalities describing the different numbers of tickets that must be sold. So we're not going to actually graph this. We're just going to practice setting up the system. This is going to be really helpful when we do the linear programming in a couple seconds here. So there are two totals that I know. First total, they must take in at least $75,000 in ticket sales. So money has to be greater than or equal to $75,000. And we know that there are fire regulations limit the number of concert goers to 3,000. So the number of people cannot be more than 3,000. So it has to be less than or equal to 3,000. So looking at those two totals, if I'm looking back at money, I know it's $30 for main floor tickets and $20 for balcony tickets. So I'm going to say 30x, $30 per main floor ticket, plus 20y plus $20 for a balcony ticket has to be greater than or equal to that $75,000 that we want to make. So before I forget, I'm just going to say, hey, I made X be the number of main floor tickets, and I made Y be the number of balcony tickets. And I also know that I can have at most 3,000 people. So that means that the number of main floor tickets plus the number of balcony tickets has to be less than or equal to 3,000. We were also told that there are up to 2,000 main floor tickets available. So that means that X has to be less than or equal to 2,000 because we only have 2,000 available. So that is our system of inequalities. Now, when we get into linear programming in a second here, these are going to be known as constraints. And the difference between just setting up our constraints like you did in Math 1, did in Math 2, did in Math 3 is we are now going to ask the question, what amount of people will maximize their profit? And then give you an actual then objective function to find a specific solution within that shaded region that will then, if our objective is maximize profit, maximize profit. So let's take a look at that. So linear programming, the objective with this lesson is to use a system of linear inequalities to model possible solutions to a real-life problem like we did, but then optimize the situation. So our objective function is something to maximize or minimize. So for example, maybe we're talking about maximizing profit or maybe minimizing cost. Constraints are all of those inequalities. So a system of linear equations or restrictions. And then the optimal solution always occurs at the vertices or corners of the shaded region. So if we have, our system of inequalities, let's say like that, I end up getting a shaded region here. My solution is going to be at one of these vertices of that shaded region, the polygon that's created by that shaded region. Okay, so let's take a look at an example. So I'm going to draw just a quick line here, and we're going to get into example 1. Suppose a candy manufacturer who makes chocolate-covered pretzels and chocolate-covered raisins wants to maximize their profit. So right now, maximize profit, I'm probably going to do some linear programming. Let's let X be the number of boxes of chocolate-covered pretzels and Y be the number of boxes of chocolate-covered raisins. This candy manufacturer makes a pure profit of $1.50 per box of chocolate-covered pretzels and $2 per box of chocolate-covered raisins. So if I'm just looking at my pure profit, I'm making $1.50 per box of chocolate-covered pretzels, which we said was X. We said that here. And $2 per box of chocolate-covered raisin, which we said was Y there. So that is our profit, or our objective function. That is the function that would maximize profit or calculates profit. Now, ideally, this company would make as many boxes as possible, but we all know that that's not always necessary. There's constraint, there's amount of hours people can work, there's only enough supplies to make a certain amount of boxes, etc. So we need to take those constraints into account. So our first constraint says, due to having only so much time per month, right, there's only so many hours in a day, the manufacturer can only make a maximum of 1,200 total boxes of candy per month. So our first constraint is that the number of chocolate covered pretzel boxes plus the number of chocolate covered raisins boxes has to be less than or equal to 1,200 because that's the most amount that we can make in a month. I'm going to go ahead and solve this for y because we are going to be graphing it, so it just makes it a little bit easier. Our second constraint is the demand for chocolate-covered raisins is no more than half the demand for chocolate-covered pretzels. To help their products sell, they keep to these demands when they produce their candies. So we know that the demand for chocolate-covered raisin boxes, Y, is no more than, so is less than or equal to half the amount of chocolate-covered pretzels. So there's our second constraint. Oop, I skipped too many. And due to the availability and cost of buying raisins to put in their candies, the amount of chocolate-covered pretzels should be less than or equal to 600 plus 3 times the amount of chocolate-covered raisins produced. So X, which is the number of chocolate-covered pretzels, should be less than or equal to 600 plus 3 times the amount of chocolate-covered raisins produced. Right now, this is not in standard form or slope-intercept form, so I'm going to solve this for y, subtract that 600 over, divide by 3, and we end up getting, oops, let me delete that, and delete that. Y is greater than or equal to 1/3 x minus 200. I'm sorry, minus 300. Wait, no, 200. I said that right, wrote it wrong. All right. And one more constraint that was not given to us, and it's just the common sense constraint. You can't have negative amount in candy, so x has to be greater than or equal to 0, and y has to be greater than or equal to 0. All right, so let's put all this together. So our objective function is p equals 1.5x plus 2y. Again, our profit is $1.50 per box of chocolate-covered pretzels plus $2 per box of raisins. Our constraints from the first scenario there, we have our first constraint, y is less than or equal to negative x plus 1,200. Our second constraint, y is less than or equal to 1/2 x. That again came from our second scenario. That third constraint, y is greater than or equal to 1/3 x minus 200 from our third constraint, and then we have those two common sense constraints. Now, when we're graphing, x is greater than or equal to 0, y is greater than or equal to 0 just means x and y have to be positive. So that means that our answer is going to be in quadrant 1. So the easiest way to kind of represent those constraints is to do what I did here, just graph quadrant 1. Cut out quadrants 2, 3, and 4. And now let's graph these functions. So this first one, y is less than or equal to negative x plus 1,200. So we have a y-intercept of 1,200, a slope of -1. So we get a line that looks like that. That's 1,200. That's 1,200. Solid line because less than or equal to, and then we'll ultimately be shading downwards because less than or equal to. Our second function, y is less than or equal to 1/2 x, so our y-intercept is 0, 0, and we're going up 1, right 2. So let's see, up 1, right 2, up 1, right 2, etc. Solid line because or equal to, and again, we'd be shading below. Our third one, y is greater than or equal to 1/3 x minus 200. So we have that y-intercept of negative 200. So we're starting down here somewhere in a slope of 1/3. So something like that. 2, solid line, shading above. And then we have the constraints of x is greater than or equal to 0. So our shaded region is going to be the part that is below the purple, above the blue, below the green, but also remains in quadrant 1. So we have this region here. So now we need to find the intersections 1, 2, 3, 4. So we already know this one here is 0, 0. So that's nice. Now we just got to find the other ones. So to find the other ones, you can do it algebraically. You can do it on your graphing calculator. It's kind of up to you whether, whatever's easier. So for example, like this x-intercept here, I'm going to find that algebraically. That's the x-intercept of that y is greater than or equal to 1/3 x minus 200. So if I just add the 200 over, multiply by 3, we get 600. So I know that that's at 600 comma 0. But these two intersections, let's use our calculator to find those. So pulling up the calculator, let's enter our equations into our y equals. So we have y equals negative x plus 1,200. Oops. We have 1/2 x. We have 1/3 x minus 200. And we don't need to put in x is greater than 0, y is less than or greater than or equal to 0, because we just know that that means it's in quadrant 1. So we are going to have to change the window, right? Because our normal window is a 10 by 10. There ain't no way we're seeing 600 comma 0 and 1,200 comma 0, right? So when we set up our window, I'm going to set it up similar to this. So I have x's going from 0 to 1,200. And I'm just going to say scale by 200. Or actually scale by 100. Why not? And our y is same thing, 0 to 1,200. Scale by 100. Don't know what I did to make that bigger, but that's nice. And now I'm going to hit graph, and let's see. So there's that first one, there's that second one, and there is that third one. So I am looking for these two intersections here. So to find those intersections, second, calculate intersection of that. See how it's dotted on the line? It tells you at the top left corner y equals negative x plus 1,200. So I want the intersection of that line. And yep, y equals 1/2 x. One more time. I don't know why you have to hit it 3 times, but you do. So we get 800 comma 400. And then I need to find the intersection of the purple and blue line. So y equals negative x plus 1,200 and y equals 1/3 x minus 200. So let's calculate an intersection again between, nope, yep, that one, and nope, jump, there we go. And y equals 1/3 x minus 200. And there it is at 1,050 comma 150. Okay, So now that we have those four intersection points, one of those values of X and Y are going to maximize our profit. So how much of each type of candy should the manufacturer make in order to optimize the profit? So there's our profit function. We have option of 0, 0, which we don't even need to test that one. There's no way that selling nothing is going to optimize our profit. So that's a toss out, which is nice. But let's test these other ones. So testing this first intersection, we have 1.5 times 800 plus 2 times 400. So that ends up giving us $2,000. Testing the second intersection, we have 1.5 times 1,050 plus 2 times 150, and that ends up giving us 1,200. And then 3, that third one, let's see, we have 1.5 times 600 plus 2 times 0, and that ends up giving us 1,875. So we got a winner here. So our answer, 800, whoa, no way can we see that yellow. Try again. 800 chocolate covered pretzels and 400 chocolate covered raisins for a max profit of $2,000 that month. All right. So very similar to just graphing inequalities. The only thing is that we're looking for, again, the vertices of that shaded region, and one of those coordinates of those vertices, those intersections, will end up being the value of X and Y that maximizes, in this case, maximizes our profit or minimizes if that's what we're looking for. All right, so let's take a look at another example. This is in our previous book. It was page 560, number 43. In our new book, there is an example very similar like it in the section 7.7 examples. I forget which example number. I think it was like example number 5. But anyways, let's go through this. So we're not going to actually go through the process of graphing this and finding the solution because what makes this problem hard is kind of the way it's worded and the wording and the setup and how you set it up. So I want to focus on that. So when you get a question similar to this one in your homework, you know how to set it up. The graphing and everything, that's just math 1 again. I think you guys will be okay with it. So a farming co-op mixes 2 brands of feed. Brand X costs $25 per bag and contains 2 units of A, 2 units of B, and 2 units of C. Brand Y costs $20 per bag and contains 1 unit of A, 9 units of B, and 3 units of C. The minimum requirements of A, B, and C are 12 units, 36 units, and 24 units, respectively. What is the optimal number of bags of each to use? What is the optimal cost? So we want to minimize costs, but while meeting those minimum requirements of 12 units of A, 36 units of B, and 24 units of C. So our objective function is C, our cost, is $25 per bag of brand X and $20 per bag of brand Y. And I know that I need at least 12 units of brand A. I need at least 36 units of brand B, and I need at least 24 units of brand C. So, how can I get units of A, units of B, units of C? Well, brand X contains 2 units of A, so 2 units of A come from brand X. Two units of B, so 2 units of B come from brand X. And 2 units of C, so 2 units of C come from brand X. Brand Y contains 1 unit of A, so I can get 1 unit of A from brand Y, 9 units of B, 9 units of B from brand Y, and 3 units of C, so 3 units of C in brand Y. I'm going to highlight where I got that from. So we have brand X costs $25 per bag and contains 2 units of A. So brand X has 2 units of A, 2 units of B, and 2 units of C. So that's what we're seeing here. That 2 units of A, 2 units of B, 2 units of C are all from brand X. And then brand Y costs $20 per bag and contains 1 unit of A, 9 units of B, and 3 units of C. So there we go. We have that 1 unit of A, 9 units of B, and 3 units of C from brand Y. So from here, it would be exactly the same. Solve each one for Y, graph them, find that intersection, and then test those points in our optimization function. In case any of you want to try it, just to make sure you got it, I believe the answer comes out to be 9 bags of brand X and 2 bags of brand Y for a maximum or a minimum cost, or no, minimum cost. So that would be, sorry, I looked at the, sorry, it was 3.6 for a minimum cost of, I think it came out to be $195. Yes, a minimum cost of $195. So 3 bags of brand X, 6 bags of brand Y for a minimum cost of $195. All right, so again, what you're going to do is you are going to go, once everyone in your group is done, push your desks into groups, go through the notes first with everyone in your group, just making sure you like grasped it, ask any questions you have, and then you guys have the rest of the block period to work on your homework. So you should get, a decent amount of time to work in class. If this was hard for you to learn from a video, I get it, it's hard. Please come see me during my office hours. I have some office hours tomorrow morning before school in person and Friday before school. So they are posted in the back bulletin board as well as posted outside of our classroom as well as posted on Google Classroom. So take a look. All right. Have a wonderful day and I will see you all Friday. Bye. Bye.